Hello, respected judges. It is with great excitement and humility as candidate for the annual STEM Project High School competition to the University of Sheffield. We are from the affiliated senior high school of National Zhongxin University in central Taiwan, and we are presenting a project on building an autonomous delivery drone. This project was done by me, Lin Youjun, my classmates Luo Yijun and Wang Yilin, under the guidance of our instructor, Zhou Shenhong. In recent years, natural disaster and epidemic caused a hard time delivering supplies to areas in need. Seeing industries like medicine and e-commerce successfully adopt drone delivery, we wonder, could we actually make it a reality and implement it ourselves? Driven by the question, we sought guidance from our instructor while studying drone technology this semester and even consulted a village head to investigate the feasibility of our ideas. So we inquired with the village head. We learned that Shehe village used to suffer from flooding and living residents isolated during the pandemic. This isolation led to a shortage of critical supplies like masks and medicine, especially for the elderly. Driven by this urgent need, our envisionment is using drone with automatic control to deliver medicines, aiming to improve the lives of Shehe residents and potentially serve as a model for other remote communities. It perfectly matches our ideas and we will make a real-world drone delivery. To successfully deliver supplies with the drone, we will utilize both the open-loop and the closed-loop control system of the drone. The drone's closed-loop control system employs a PID controller to stabilize its flight, while the open-loop system relies on the ground control system to autonomously execute commands. Let's take a look at how closed-loop system works in drone. During flight, winds might push the drone aside, or the propeller might not work exactly as expected, causing slight changes in thrust and rotation. This can make the drone go slightly higher or lower than the desired position. This picture shows how the closed-loop system works. The quadcopter keeps measuring its rotation, comparing it to the desired rate, and making corrections over and over, constantly adjusting to stay on track. The quadcopter's brain, called PID controller, uses a special formula to figure out how much power to send to the motors to correct any differences. P in PID stands for proportional and mainly controls sensitivity. I means integral and prevents the P-term from causing oscillation by reducing its impact. D means derivative and helps the controllers anticipate future changes. By adjusting the PID parameter, we can fine-tune the drone's control system from optimal stability. The controller constantly sends commands to the motors telling them to speed up or slow down to match the desired rotations and altitude. These adjustments bring the drone closer to the desired state. The process repeats continuously, ensuring smooth and accurate flight. This is how the PID controllers work. We will build a drone and adjust the PID parameter to stabilize it according to our needs for this project. For the open-loop control system, we'll use Mission Planner, a powerful ground station application for open-source autopilot project. It allows us to plan and adjust open-loop commands to suit our project's needs. We'll delve into it in detail later. First, let's reveal how we build the drone and implement our project.
Our project is centered on an open-source ground station system. Required us to procure parts and construct a drone from scratch after consulting with our instructor. The entire assembly process proved to be challenging, encompassing tasks from comprehending individual parts and the drone's operating system to the actual construction. In addition to the basic drone, we incorporated extra features such as LED light for direction indication and a gripper for manipulating objects. Following assembly, we conducted calibration for horizontal and vertical setting, checked transmitter functionality, and adjust flight mode. After thorough pre-flight check, we proceeded to the playground for an initial test flight. Despite our careful assembly, we felt apprehensive, anticipating potential mistake. As expected, the drone flipped during its maiden voyage. Frustration and disappointment were unavoidable, but with guidance from an experienced instructor, we made necessary adjustments. Only then did the aircraft fly smoothly, ready for setting up a closed-loop control system. A PID controller regulates the drone's closed-loop control. Our goal was to find true parameters for improved stability and responsiveness. Collaborating on the computer, one person adjusts parameters while the other controls the drone's yaw, roll, and pitch. We found that an excessively high p-value led to oversensitivity, causing difficulty in balancing and dynamic error in altitude maintenance, resulting in erratic up and down movement. Conversely, a low p-value made the drone sluggish and unresponsive to user input, lacking the necessary power to react adequately. In such instance, increasing the p-value was necessary. Personally, I encountered a challenge with joystick drift after returning to the center position, indicating a low I value that required adjustment. Gradually, we fine-tuned the drone for slow, controlled flight, ideal for our delivery mission, marking a significant milestone. The next phase involved testing the open-loop control system.
We chose our school for initial testing due to its spacious environment, minimizing potential risks. After confirming successful completion of all setup tasks, we will move to the village to carry out the real delivery work. Our automatic control stages are takeoff, waypoint navigation, landing, cargo release, another takeoff, return to launch. These commands require parameter setup and testing. To ensure successful completion of the entire automatic process, we encountered many challenges in resetting on this open-loop system. Among these, accurate GPS coordinates are the most challenging aspect due to the wrong position of our modules. Incorrect coordinates could lead to an accident. Additionally, setting a release gripper presents another challenge. It must be wired correctly to communicate with the flight controller and receive cargo release signals. Failure of either the GPS coordinates or the release gripper setup will jeopardize the project's success. After confidently setting up and testing the commands, we moved to the village and selected 2 locations for our delivery project. However, the real-world deliveries were challengeable. At the first location, power lines and limited landing space due to them poses unforeseen challenges. Despite encountering a manufacturing gripper and a drone deviating from the planned landing point, we repeatedly adjusted the landing coordinates on the ground station and successfully delivered a simulated package on our first attempt. Building on this experience, we tackled a more challenging location requiring the drone to fly over several buildings. Thanks to the valuable lessons learned from the first delivery, we completed the second delivery in around 15 minutes. With an automatic drone control system, we successfully completed this project and solved the problem of difficulty on people getting supplies in remote areas. The feasibility and reflection stated as follows. The major challenge lies in GPS inaccuracies due to the limitation of our lower accuracy equipment. While expert drone companies can certainly develop high-precision navigation drones for such applications, the dense urban environment in Taiwan will present significant challenges, potentially limiting the project's suitability to remote areas. In the context of our project, we initially considered drone delivery of medicine. However, delivering medicine efficiently requires collaboration across different departments. We propose that hospitals handle diagnosis, prescription, and preparation, while the fire department handles drone operation. This collaboration will enable efficient transport of medications to designated locations, minimizing risks to medical personnel and improve overall efficiency. Unfortunately, can drones find obstacle-free landing spots in disaster zones? Our successful experiences also highlight that drone operations, like takeoff and assembly, pose significant challenges. Can drones truly achieve expected effectiveness in real-life situations? On the other hand, While automation can make things more efficient and less labor-intensive, unlike humans, automated systems, even with feedback and correction systems, may not adapt well to unprecedented situations. In such cases, can errors occur in the machines? This is a question worth pondering.